Um, yeah, it's one that is good, right?
All right. Okay. Hi, everyone. Let's go ahead and get started. Thank you so much for joining. This is the first Frontiers in Quantum Information and Technology seminar. So this is a seminar joint with Michigan State, University of Michigan, and Purdue through the Midwest Quantum Collaboratory. So today we're very excited to kick it off with MSU's own Jeff Schenker. So Jeff is a professor and chairperson in the Department of Math with interests in mathematical physics and quantum information. Today, he will tell us about the theory of ergodic quantum processes. And before I turn it over to Jeff, for people in the Zoom, the best way to ask questions is just through the chat or the Q&A, whichever one you like. And I'll be monitoring that and calling it out to Jeff. So without further ado.
All right, thank you, Ryan. And actually, maybe I will turn my video on for the Zoom people so they can, I don't know, see my face. Oops.
Reduce the number of boxes over there.
Oh, there we go. There we go. Yeah. All right. So thank you. I'm happy to give this talk. And I want to give you a slight warning beforehand because I realize that this is a very mixed audience. I am a mathematician. And so in particular, the use of the word theory here might be a little bit of a stretch because good theory should be predictive, and I think what I'm giving you is a little bit more descriptive. So just this is a work in mathematical physics, but I think it has points of contact with theoretical and potentially even experimental physics if the right conversations are had, which is one of the reasons I'm quite excited to give this talk. So I hope that this generates questions and further discussions. And please interrupt if you have questions. I would be happy to stop and answer them. So let me also mention my collaborators, Ramis Movasag, who is now at Google and was just here last week. Some of you saw him give a couple of talks. He wrote 2 papers with me that most of this is based on. And then I have several students who are sort of working on extensions and additional ideas. One of them graduated just last year. And one of his papers is mentioned here. He's now a postdoc at QMath in Denmark. And I have 2 students, Owen Ekblad and Eloy Moreno-Nadales, who aren't able to be here this morning, but are working on aspects of this work right now. And then Reynel Rekepa is a postdoc at NYU, who I have another project with that started when we saw each other in France, actually, a couple of summers ago. So, okay. Oh, I think maybe I'm on the Zoom window. There we go. Okay, so I want to first, the talk said theory of ergodic quantum processes. So first I should tell you what I mean by a quantum process. And I'm using the word in a fairly precisely defined sense, even if that's not a standard, or the words, even is not particularly standard. So the idea of a quantum process is that we look at a system and we let the system evolve under a sequence of potentially different evolutions that are quantum channels, so they may involve the effective interaction with an environment. Okay, so we just have basically the quantum process is a sequence of quantum channels. Now, I remind you what a quantum channel means. It is a completely positive trace preserving map. So essentially, it is the evolution of an open quantum system reduced for the reduced density matrix of an open quantum system, written here in Krauss form with the Krauss operators, and the Krauss operators should satisfy this identity, that they sum up to the identity so that we have this trace preserving property. The fact that it's in this form gives us this completely positive form for it, which is a necessary and sufficient thing for being the evolution over a discrete unit of time of the reduced density matrix. Okay. And obviously, there's a missing arrow between here. This should be going from here to here to here, right? So, okay, so that's a quantum process. So here are some examples of where these might come up. So you may have a system that is interacting with a series of ancillary systems. So you bring in the first ancillary system and an interaction occurs. And maybe on its own, there's no, there's no decoherence, right? The evolution is purely unitary. So the ancilla comes in, the state, because there was no interaction beforehand, no entanglement between the system and the ancilla, is just the product state. That product state evolves according to some joint Hamiltonian for the system and the ancilla over some unit of time. Doesn't have to be the same amount of time for each one of these. Once the ancilla is done, perhaps we discard it, right? It flies off, it's incinerated, I don't know what happens to it, and we forget about it, and we're left effectively with an evolution for the density matrix of the system, okay? That's one way such things could arise, and one thing you could imagine. One important thing to note about this is that there is a subtle little assumption that's being made here. Notice I'm talking about a sequence of ancillary systems. If I talk about something interacting over and over again with the same system, then there's a small problem with doing this, that there is back reaction that can't be accounted for in this formalism. So life can get much more interesting, of course, if you have the same system. Of course, if it's a thermal system and what's coming back to you tends to be thermalized and you can make a Markovian ansatz, then it makes sense. Then this also applies to that. But there's a reason why I said a sequence of ancillary systems. Okay. Another and actually quite similar way that this comes up is in the theory of repeated measurements. So you can imagine that I have a system and it evolves for some time, and then I perform some sort of generalized measurement, maybe by some procedure through that was like on the previous slide. So one of the famous sort of examples of these repeated measurement things were the experiments that were done with cavities and atoms flying through them, and optical cavities. I was grabbing for the word optical and couldn't find it. And you measure you do an effective measurement of the cavity by looking at the atom after it flies through. And you can understand that in something a bit like this formalism here, where there's an evolution, and after the evolution, we perform a generalized measurement, maybe not a projective measurement, but we have a sequence of finite set of measurement operators. And the probability of getting an outcome is just the trace of the density matrix at time t. Yeah. I think I must too. So at time t, the density matrix is the evolved density matrix. We make a measurement. The probability of achieving outcome R is given by this standard expression, and the density matrix is then known to be in this state by the assumption that we get a collapse of the wave function at that time. Okay. So, and if you look at the average over quantum measurements, you get back to the same thing. So if we average over the results of measurements, we have a process. So you can sort of tongue-in-cheek say that if you forget the result of the measurement, then what you have is the quantum process. Of course, the system is actually in a different state than given by the process, but the density matrix of the process sort of describes then our uncertainty as to what it's in, because we haven't recorded the measurement. Okay, so those are two examples of quantum processes. One can generalize this a little bit. Sometimes it's interesting to take maps that are not trace preserving. So perhaps the system, perhaps sometimes the experiment just fails and we have to dispose of the system. And that in that case, the density matrix is sort of effectively not, the trace is effectively not preserved. And another thing is in the realm of the repeated measurements, maybe you want to compute some certain expectation values. You don't want to just take the average density matrix. Maybe you want to take the average outcome of the measurement. Maybe each outcome is associated, with an energy lambda r, and you want to compute something like this, which would then be a moment generating function for that energy. And now, effectively, you replaced your Krauss operators by e to the alpha over 2 times the Krauss operators times lambda, e to alpha of 2 times lambda r. And now the map is no longer trace preserving, although it is completely positive. So it's interesting to look at the situation where we don't demand them to be trace preserved. Okay, so we'll take a we'll use the word quantum process to just describe a sequence of completely positive maps without assuming trace preserving. And what we're interested in is the long-time behavior of the composition of the maps. And of course, without telling you something about what the maps are, I can't tell you something about the long-time behavior. But what I'm going to do is show you something that is a general answer to this question for something that I'm glibly calling irreducible ergodic processes here. I'll define the word ergodic and I'll give a more precise meaning to what I mean by irreducible. And I'll show you that in this situation, we actually have a relatively simple and general limiting behavior. We can take limit, we have certain limit theorems for the expectation values. We can come back and say something about repeated measurements, and there's actually an application to disordered matrix product states. And actually, it's nice to, so of course, the way works get presented is usually very different from how they came to be. And actually, it's exactly the opposite there. So Ramis Movasad came to me with a question about disordered matrix product states. And we started discussing it and like, how could we prove things? And in the process of doing that, we realized that we had come up with something, a structure that was applicable to a widely different array of problems and actually interesting on its own right. So the application at the end was actually the original goal, but it's not the most exciting thing to come out of it, I would say. So, okay. So now I'm going to do a little bit of math, classical mathematics. Well, not quite classical because I'm going to apply it in a slightly non-classical situation related to the Perron-Frobenius theorem. The Perron-Frobenius theorem is the famous theorem which tells you that if you have a matrix with all positive entries, then it has a positive eigenvalue with an eigenvector that also has positive entries. Okay? And that eigenvalue has to be at the spectral radius of the matrix, et cetera. Okay, so suppose I have a map that on the D by D matrices that is positive. Okay, well, what that means is that it takes a positive matrix where positivity means in the sense of quadratic form, so positive definite, and returns a positive matrix. So completely positive maps are in particular positive. They're a little bit better than positive because they remain positive when you tensor product them with the identity on other spaces of matrices, and that's a technical condition which we don't need to worry about. So positive maps satisfy a version of the Perron-Frobenius theorem. And this is most easily found in a paper of Evans, Hugh, Krohn from '78, but it relies strongly on results from Crane and Ruttman that appeared in the 1950s and are available in translation, but not online. I actually had to get the volume from the library. A lot of the journals of translations are available online, actually, from that time, translations of the Soviet journals, but this particular volume was not. So I'm not sure why. So if the map is irreducible and aperiodic, those are things which I will define on the next slide, then there's a unique, strictly positive density matrix. Strictly positive meaning it doesn't have 0 as an eigenvalue, so it's full rank, such that that's an eigenmatrix of the map. And lambda is the spectral radius of phi. That is, any other eigenvalue of phi is actually strictly less than lambda. Okay. Spectral radius is less than or equal to, but in this case, it holds that any other eigenvalue, there's a spectral gap, that there are no eigenvalues on the circle of the spectral radius except for this Perron-Frobenius. So for those who have some experience with Markov chains, there's a similar theorem for the transition matrix of a Markov chain. Do you have a question?
Yes.
Yeah.
Well, I'm just kind of confused by this actually. Is the way you define phi, I mean, as you said, it looks more like a positive definite matrix. Or like a positive definite map.
Right. So it is a positive map. Right. So so the situation is this. So a positive matrix is a matrix that one way to think of it is that it preserves the cone of vectors that are positive. Okay. The positive definite matrices also form a cone.
Okay.
And a positive superoperator is a linear operator that preserves that cone. And in fact, this Crane-Ruttman paper is a very general set of results about operators on Banach spaces that preserve cones. And there are conditions under which you can find an eigenvector in the cone. Okay, so
yeah, I mean, just thinking more naively, when I think about like, matrices acting on vectors, I mean, a matrix with all positive entries and a matrix that's positive definite are not at all the same thing.
they're
right?
not at all the same thing, but notice
There's
here
something
that
more interesting going on.
positive definite here is the matrix A, which is the thing that is acted on.
Right,
Phi is a super operator,
right.
which is acting on matrices. And so this A is the thing that's like the vector. And there is a sense in which the positive definite matrices are like the positive vectors in the sense that they are the things in the, so the vectors also have an algebra. You can multiply two vectors together just by pointwise multiplication. The positive ones are the things that are a square.
Yeah.
So you can identify from the algebraic structure what is positive, and that actually plays a role in all of this. There's actually C-star algebras underneath some of this, but
very naive thing. Speaking of Markov chain, you have a stationary distribution at some point. And so when you are saying that lambda is the eigenvalues are all positive and there is a gap.
right.
But is there a zero eigenvalue?
No, so this is maybe, there doesn't have to be, but lambda equal, the eigenvalue you're interested in is 1. That's the stationary one. Because I'm not looking at the generator, I'm looking at this discrete type, right? So it's the exponential of the generator, right? So 1 is the, and here, because I haven't assumed that it's trace preserving, it might be losing mass or gaining mass. And so that's why lambda is not, but this lambda is the stationary. Okay, so essentially the result I want to tell you about is a generalization of this theorem to processes. But first I should tell you what the terms meant. The irreducible. Well, I said I defined irreducible, but then I'm defining strictly positive, which is actually a clearer thing here. So, well, no, it comes right in a moment. Phi is strictly positive if it maps any density matrix to a non-singular density matrix. So positive means it could map a rank 1 state to a rank 1 state as long as it maps, positive semi-definite operators to positive semi-definite. Strictly positive means that whatever you hand it a vector state and it's going to hand you back a density matrix with full rank. Okay, so it's looked at from quantum mechanics, it's a strong decoherence assumption, right? It doesn't preserve rank 1 states, and it does so in sort of the maximal way it could by it's not giving you the totally mixed state, but it's giving you a state that is full rank. Okay. So the irreducible and aperiodic is equivalent to phi to the n being strictly positive for some n. And this is, if you know something about Markov chains, is equivalent to the transition matrix eventually being positive in all entries. Okay, so this is a generalization of that. And I call this no selection rules because it means there aren't separate subspaces which, right? I mean, if you look at what selections rules are in like spectroscopy, it's forbidden transitions, and the transitions here are things that are taking place due to our decoherent evolution in the density matrix, and there basically aren't any forbidden transitions here, right? You can eventually get from any subspace of the Hilbert space to any other one by the transition maps is sort of what's going on. Okay, so the version of the theorem I stated is in this. Now you can ask for generalizations, and there are generalizations if it's reducible, and if it's, so the aperiodic involves no eigenvalues on the unit on the circle. The irreducible means none of the no invariant subspaces, and you can ask for generalizations, but that's not where I'm headed today. So it's a very strong condition, but I would like to also point out that it's a generic condition. If you write down a random completely positive map, it will have this condition. You actually have to fine-tune things to get eigenvalues on the circle, or to have an invariant subspace. And you make small perturbations in a general direction, and you will kill both of those things. Okay, so what if we now repeat a single quantum operation? Okay, well, as phrased, this, of course, would include the unitary evolution of any closed system. And by the way, unitary evolutions of a closed system are never irreducible, nor are they aperiodic. In fact, they're most definitely not aperiodic. All of their eigenvalues are on the circle. right? And every eigenstate of the Hamiltonian, the projection of that is an invariant state for the unitary evolution. So the unitary evolution of a closed system never satisfies the assumptions above. Another thing that comes up is that if phi is not trace preserving, then phi of rho may not be a density matrix. And in fact, if you look at the repetitions, they're going to go to 0 or infinity. And that's not very interesting. I don't want to tell you about that. So a natural thing to do is to look at the projective action where I will divide by the trace. So even if the map is not trace preserving, I can make it effectively trace preserving as long as it doesn't map a density matrix to something that is trace 0, in other words, 0. And notice that the eigenvector that I told you about on the last slide is a fixed point of the projective action, right? If I divide by the trace, I just end up dividing by the eigenvalue. So I get the eigenvalue top and bottom, they cancel each other out, and I just get rho back. Okay, so if I have an eigenvector, then it's a fixed point of the projective action, as long as it's an if I have a density matrix that's an eigenvector, then it's a fixed point. And a corollary of the Frobenius type theorem that I told you above is that if we have a positive, irreducible, and aperiodic map, then the projective action converges exponentially fast to this particular equilibrium state for any initial density matrix. Okay, so there's a simple idea of convergence to equilibrium for as long as you have this irreducibility. Unique state, yes.
I think for aperiodic, you had for any n greater than some n naught. Is n naught allowed to grow with the size of like rho here, or is it a constant?
Well, there's this size of rho is fixed, right? Phi, because phi is fixed. So I've fixed a system, right? And I've fixed a map.
Okay.
Right. Yeah.
And this is essentially a consequence of this gap.
Yes, that's a consequence of the gap. Exactly. Okay. Okay, so now that's all sort of very classical stuff. Let's try to see what we can say about a sequence of maps that are not the same. So that's repeating one map over and over again. What if I provide a process that's a sequence of different maps? So I need to give you a little bit of math structure. There might be more pedagogical ways, but they'd be much slower. So an ergodic dynamical system is a probability space. So just think of some set and a measure on it, which is a probability measure. So we have some way of expressing probabilities. And we also have a map on that space. So a way, which you can think of as a dynamics on that space. So it's a way of going from one point to another that is probability preserving and ergodic. Okay, probability preserving is relatively straightforward. The probability of a set is the same as the probability of the shifted version of that set. So, and ergodic means that the only invariant sets that you have are those that are either measure 0 or 1. Okay, and of course, there's a reason, right? This is related to Boltzmann's ergodic hypothesis about the evolution on the energy shell of a Hamiltonian system, which of course is probably not strictly true. There, the measure would be Liouville measure. It doesn't matter. There are plenty of examples of ergodic dynamical systems that are relevant, and this is a whole field of probability theory in its own right. And I'll give you some other examples. Actually, another example that's important to keep in mind is that omega could be a probability space on which I use to model a sequence of independent, identically distributed random variables. And then the t is just a shift of that sequence. So if I have a sequence of IID random variables and I shift the sequence, say throw away the first random variable, I get something that has the same distribution as what I started with, right? If I flip a coin infinitely many times and forget about the first coin flip, I still have infinitely many coin flips, right? And that map is actually ergodic. The only invariant sets are in fact measure 0 or 1, and that's related essentially to the law of large numbers. And Birkhoff's ergodic theorem is a general statement about time averages versus ensemble averages for precisely ergodic maps. And this relates it, this is sort of a justification of using the word ergodic in this context, right? If I'm going to call if something's going to be called ergodic, it should involve time averages equaling spatial or ensemble averages. And that, in fact, is the case. If I have an ergodic map of this sort, then the time average of any random variable along trajectories of the map is equal to the ensemble average, at least with all the probabilistic fine print that you need. The words almost everywhere have to appear somewhere because it's just a set of full measure where it happens, and the function has to be nice enough that I can do the integral. Okay. Okay, so that's an ergodic dynamical system, and I'm going to assume that we have one sitting for us to use. And without loss, you could think about a sequence of IID random variables. And an ergodic quantum process will be a sequence of completely positive maps that are actually random maps. So they're random map valued, they're CP map valued random variables on this ergodic dynamical system. And they're all related to each other by this shift. Okay, and I realize that's actually pretty complicated. Once you're sort of in this ergodic, probability theory thing, one understands the structure. So you can simply think to yourself that the phi j are independent, identically distributed quantum channels, and that is an example of this. Okay, so you just have some distribution on the set of quantum channels for your space, and you pick a sequence of independent channels with that same distribution. So of course they could also be the same map repeated over and over again. My probability space could consist of one point. So that's this first time translation invariant processes. They could be that. They could be IID channels, but they could actually have quite strong correlations, right? This ergodic, having the shift does not require them to be independent of each other. They are required to be identically distributed because of the shift, but they don't have to be independent. And they could have fairly strong correlations. They could actually be things that really don't fit the definition of random. They could be quasi-periodic processes where the omega is a torus of some relatively low dimension, and irrational rotations are involved. I don't know of a good example of why one would want to consider such a thing, but it is possible.
Strong correlations. What is the dependence in sequence?
Well, look here. You can get all the way. No, it's because you can get all the way down to this, where the correlations are actually incredibly strong, where you have this, where you have.
But if you have just a single process, just limit of strong correlation is just when you have just one map.
Right, that's included in here. So the correlations can be quite strong. I'm not putting a limit on them. There's no. I don't need to discuss what the correlations are.
No,
for
but
this.
You have just a single phi j.
Right.
And you repeatedly apply it.
Yes.
And for example, again, if you cannot excluded unitary transformation.
I haven't yet, but I'm about to.
Okay, because unless you do it,
right. So no. So I'm defining an ergodic quantum process. I'm going to define one more term. Okay. But I wanted to do an example before I do that to give you something to think about. So suppose we have a single qubit with its state in the usual block sphere representation. So here's an amplitude damping channel in the z direction with a rate gamma, and hopefully I didn't miss any typos. I think it looks good. Okay, right. So it's basically making a transition. Some probability of it making a transition to the ground state, right? Now you can also consider the amplitude damping channel in the other direction. The ground state of a Hamiltonian with this magnetic field pointing off in some other direction, and you can work out what that is. It's a good exercise to give to undergraduate students to do this because there are the easy and the hard ways to do it, right? Okay. So the Perron-Frobenius eigenmatrix of this amplitude damping channel is just the state that points in the direction that, the ground state of the Hamiltonian, because that's what you're eventually transitioning to. Okay. But what if we randomize W and we repeat amplitude damping with different directions? Okay. Well, here are some examples of that. Okay. So so on the left here is, so every time I started here at the, I think the eigenstate of the poly X matrix is here at the plus sign. So, the vector on the block sphere 1, 0, 0. This is a sequence of random, independent, identically distributed channels. I believe they were uniformly distributed over the whole, with the amplitude damping direction was uniformly distributed over the whole sphere. Okay? And not surprising that it's a fairly decoherent sort of thing. Right? It's pushing it down to some sort of distribution blob that's here in the middle. You can sort of follow the dynamics, right? It's a little bit hard to see in some of the pictures where the dynamics is because everything's on top of each other, but the darker things are out on the edge of the sphere, the lighter things are in the center, and you can sort of follow that this is proceeding on a path toward the center, but it's a little bit hard to make out exactly what the path is. But anyway, it is converging to something. Now, this is a very different situation. So this sequence of channels is one in which the amplitude damping is always on the equator of the sphere, but the way it changes is it makes a random walk. Either it stays put, so at each step I either use the same direction that I used in the last step, or with a certain probability I rotate it, but the angle that I rotate it is an irrational multiple of 2 pi. So it never comes back to where it started. Okay, and you can see here that the behavior is very different, that the map keeps coming back out to the boundary of the state keeps coming back out toward the boundary of the sphere and then going back in. It's never getting very small. It has some strange and interesting bowl shape. I'm not going to describe why any of these things happen, right? So I'm giving you a descriptive theory of the whole thing, but I'm just trying to say that there's something interesting going on with dynamics in all of this. This is a Markov chain. I said quasi-periodic, but this is a Markov chain. So I don't know that the irrationality was, the irrationality wasn't important there, I think.
How does it come back out? I thought your process kept making the.
No, because the amplitude damping channel, an individual amplitude damping channel wants to put it out to the boundary because its invariant state is on the surface.
Oh. Right.
And so what's happening here, what's happening in the first one, what happening in the first one is that I keep choosing a different direction to try to normalize to, and it never has time to catch up. But here, because I'm sort of slowly proceeding by small increments, it has time to catch up, but then eventually some noise picks up and it pushes it toward the middle and it keeps trying, it keeps competing. This one's the quasi-periodic one, where at every step I choose a new direction, but the angle increment is irrational.
Unit direction.
Right. If it's rational, so this one is done by choosing a rational rotation and then looking at a stroboscope. So this is just repeating at multiples of the period for a rational rotation. I need to do 2 amplitude damping channels in a row because one amplitude damping channel is not strictly positive, is not because the invariant state has rank 1. But 2 of them at different angles in a row actually is strictly positive. And so if I use a periodic map, then I get something that shows an example of that convergence to equilibrium for just the Perron-Frobenius type behavior. So these are the sorts of things you can get. And the thing I want to point out is that we're not going to go to a limit. We're going to go to a statistical limit. There's going to be a distribution that we're converging to. Okay. And we're going to need an assumption, and this gets back to your question, Mark. So we're going to assume that the process is eventually strictly positive, ESP. In other words, there is an n naught such that if I go beyond that point, then the process is strictly positive with probability 1. Okay. And we need this to get the uniqueness. If the map T, the ergodic map, is invertible, which basically you can always assume it is, because there are nice procedures for lifting a non-invertible one to an invertible one, then this is equivalent to 2 computable assumptions, namely that for some time, it is strictly, that the probability of being strictly positive is positive. And when I say computable, what I mean is that they can be verified by a finite computation. They can't be falsified, right? But at least, you know, if for some n naught I can verify that this probability is positive, then I'm in good shape. And then the individual maps should be faithful, so it shouldn't map any density matrix to 0. This never happens for channels because they're trace preserving. And it's what I call one-step non-transient. In other words, the transpose is faithful. In other words, it doesn't have any subspace that's a transient subspace after one step. So an example of something that would be that is if I took the amplitude damping channel and I tuned the damping parameter to 1, then I'm immediately in one step going down to the ground state. And so that would have the transpose would actually have would have a 0, and a density matrix in its current. Okay, so I'm going to make this assumption that we have a process where eventually we get strictly positive. Okay. It's not actually a particularly strong assumption in the sense that all you need to do is get strictly positive over some finite time with positive probability, and then the ergodic nature carries over and actually forces the thing to be strictly positive eventually with probability 1. Okay.
That is something that is confusing to me, because when I think about the dynamic prognosis as relaxation, I know that I cannot invert it.
The T, yes. So but there's a mathematical trick for doing the inversion, right? No, so I mean, you obviously you have to change the space in which it's acting on. Basically, what you consider is not the space itself, but the space of all trajectories of the process.
The space of the trajectories.
Yeah. And the conditions are ones that mean that space of trajectories is a nice enough space to look at. So, and then you can actually invert. Okay.
Which is a big problem because the space becomes infinitely.
Yeah, but remember, I'm thinking about IID random variables really as my main example anyway. So I'm already in an infinite dimensional space. So it's and there, right? I mean, if you define a forward-looking sequence of IID random variables, formally the map is not invertible, but all you have to do is extend your sequence backwards in time with IID random variables in the other direction, and all of a sudden it becomes invertible. And so we can talk about
it.
Yeah, right.
One of the major points of relaxation, you're talking about discrete transitions between states, essentially. There is a rate of this transition, but you don't know when they happen.
Right.
And therefore, then in the quantum process, if you want to know when this process happens, then you have violated quantum mechanics.
Yeah, but remember, T is an auxiliary object that's living on our probability space. It's not the process. Okay, but yeah, it's a technical condition, and then I claim in all the interesting examples I know, you can make it invertible. I have to go to some very strangely cooked up measure theory examples to find things where I can't do this.
Well, you have to tell me.
Right.
Just with the two-level system of switching between the two states, how you do it.
Yeah, but okay, yeah, right. No. You'll see, because we're talking about completely different things. Okay, so we actually expect this assumption to hold for any process once we restrict it to maybe random reducing subspaces. Okay, so right, it's an irreducibility type assumption. The process ought to have a decomposition into irreducible subspaces if it is reducible. And this is actually something that my student Owen Ekblad is currently working on. And I think we'll actually have a paper out pretty soon where we understand how to take a more general such process and decompose it into its irreducible components. Okay. And here's the theorem, finally. So suppose I have an ergodic dynamical system with this invertible map, and I have an eventually strictly positive ergodic quantum process as I've defined, so the sequence of random channels. Then there's this density matrix valued random variable, Z, that lives on my probability space. So for each realization of my disorder, I get this density matrix random variable. And if I look at the translates of this Z along the ergodic dynamical system, so I take these, I define Zj to be Z translated by T to the J omega, T to the J. Then, in fact, the process for any initial state is converging to this Zn. So basically, the process forgets about its initial state. All it knows about is the noise that it's been handed from the ergodic dynamical system. And the only information you need is this Zn. And it just sort of eventually follows the Zn. Okay, so I want to claim it's more complicated looking, but it's it's actually a direct analog of the result we had about convergence for iterating a single map. It's just that here you're moving to a statistical distribution of maps, which actually change from time to time, but they have a well-defined distribution. Okay. And so the heart of the proof, let me just say, I'm not going to, this is not a math talk, but I should say something about a proof. I can't, is a contraction argument that shows that if we take the Perron-Frobenius eigenmatrix for a long chain of these guys, that these Perron-Frobenius eigenmatrices actually converge as we take the initial time way back to minus infinity. Okay, and that's what's going on at forward time. At large forward time, we're basically almost in the case where the system's been running infinitely long. And so we expect it to be in the state that it would have been if it had been running from time minus infinity. That's okay.
So this is also somehow related to the gap at zero.
There's a gap here at zero of something, and actually, my student and I have clarified what there is a gap of. It's not a particular matrix or operator now. It's small dimensional. It's some operator on a Banach space of matrix density matrix random variables that actually does have a gap. So yeah. And there's a similar result for the left eigenmatrices. So there's another thing called Zn prime, which will come back if I have time, although I'm going pretty slowly. So as I said, there's this, right, I've already sort of said what's on this slide. There's this, that for each disorder configuration, the sequence converges to the unique equilibrium, which is a process that's driven by the system. And it has, we can characterize it statistically, but we can't characterize it as an individual point. And this generalizes the eigenvalue equation in the translation of variables. Okay, so this is something I will say, but I'm not going to give you the example. For independent identically distributed channels, it's actually in principle possible to solve the shift equation for the distribution of this Z. And Ramis and I give an example of that, at least in a large system size limit in our paper. So that you get a nice equation for the distribution, and you can actually solve it under suitable assumptions. So okay, so I can either tell you about limit theorems and applications to quantum measurements, or I don't think I have time to do both. I guess I'll just go ahead and I can talk, because the matrix product states is kind of, as I said, an orphan in here. It's only here because it's the origin story, not so much the reason. So, okay, so, and this involves other work done at MSU, so I should write by students here. So this is my former student, Lubushan Pathirana, who's postdoc at QMath in Denmark now. As part of his thesis, he looked at sort of law of large numbers for these processes, which is phrased here, although I have to say it's sort of, it's kind of opaque looking to me what this means exactly, so it may be best to go on to the next slide. So basically, we look at the composition of this ergodic process, and it has this eventually strictly positive assumption, and there's the ergodic probability space and all of that. And we look at the evolution of a density matrix, and then I hit it with another state of trace one, which is kind of a weird thing to do, because really I should be hitting it with an observable, so maybe that's an operator of norm one, but I'm in finite dimensions. So, and I think I maybe forgot to say that at the beginning, that everything here is in a finite dimensional space. that's somewhat important, and I'll get to that in a bit. And so I can normalize any positive thing to be trace one. And I look how big can this trace get? And it actually is guaranteed in this context to either grow or decay exponentially. And there's a Lyapunov exponent, which you can actually relate to the equilibrium. And this is, we call this a law of large numbers. There are reasons in the proof why it actually looks like a law of large numbers.
Big N equal to little n, or is big N something else?
Oh yeah, big N here. This is right. That's big N.
Okay.
Yeah. Thanks. Good eyes. What is phi naught is the process at the origin. So at time zero. So it's just phi. I think I called it phi on a previous slide, but it could be any of the other ones because they all have the same distribution, but you just have to pick one in the average. Okay. Again, capital N here. This is not an interesting statement for quantum channels because they're trace preserving, and so you can actually see that this quantity is bounded, particularly because we're in the eventually strictly positive case, that this thing becomes bounded away from 1 and 0, and so the limit is just 0. The Lyapunov exponent is 0. But it is interesting for non-trace preserving processes. Because it gives us a way to compute this Lyapunov exponent in terms of the invariant state. There's also a central limit theorem for the next sort of level of fluctuations, but that's more technical to state, and I don't know an application of it yet, so I'm going to skip over it. But I do have an application of this Lyapunov exponent. So if we go back to the repeated measurement process, and so suppose I have a fixed set of outcomes, and I do a repeated measurement process. So I have some random matrices that describe my measurement process. And these don't have to be very random. They just have to have an ergodic distribution. So the thing I really have in mind is that you're trying to do a repeated measurement process with fixed measurement operators, but maybe the transit time of the atom through the cavity is slightly different at each step, and that's some intrinsic randomness that you can't control for. But hopefully it's coming with an ergodic distribution. It should if they're independent and identically distributed. Maybe your instrument, maybe there's a little earthquake going on and your instrument's shaking. Well, that's probably less ergodic. But right, and so we do this measurement, and we get the repeated measurement process, and right. The outcomes are some real numbers, and maybe we want to understand the average outcome or the distribution of the outcomes. And one thing we could try to do is, I think the W here should be the Q. This should be Qs. Oh, the W's are random variables that take values of the Qs. That's why I have that here, but I haven't told you what. Oh, here it is, right? You measure Wj equals QR with probability. There we go. So if I look at the moment generating function for sums of these, then it's actually exactly a process of this form as I described before. And we now know how to compute this Lyapunov exponent. And it's related to this statistical equilibrium. And actually, this is this work that I have in progress with René Raquepa. In progress here means that, we know how to do something, and I'm department chair, and so I haven't actually looked at the things he sent me to proofread yet. But I guess that's in progress. We have we've established differentiability of this Lyapunov exponent, which then by very standard methods, off-the-shelf methods, implies a large deviation principle and lets you start talking about things like entropy production in the measurement process and all of it. So it's I think a kind of cool application. And it only requires, some previous works on this had required independent, identically distributed. We don't need that. We just need the ergodic, right? So we can have correlations between our things as long as we have this ergodic structure. It's also interesting, so there's a whole dichotomy when you look at the specific outcomes, not the average outcomes for repeated measurement processes between, many times the measurement process actually has purification, right? When you do the repeated measurement, you drive the system to a pure state. When you average over outcomes, you get a density matrix, but the individual state that the system for any realization of the measurements is being driven to is it becomes pure. In fact, after looking this well, I believe that that's a generic condition, although I've talked to some experts and nobody seems to know how to prove that. And then there are these flip cases where you don't have purification of the process, where there are these so-called dark subspaces that emerge. And we're trying to focus on understanding that. So the previous work has really understood this in the context of just a single repeated measurement process. So the only noise is the quantum randomness from the measurement. And we're working to understand this dichotomy in the context of these ergodic systems. And I think we have a good understanding of it. The interesting thing is that certain projections that you're interested in become random, and it's a bit more complicated to analyze. And as I said, there's a little bit of literature here from previous work that was done on these in the IID case, or in the deterministic case. Okay, so I only have 7 minutes left. Is it 1 hour or a 50-minute seminar? 1 hour. There's something I really want to show you at the end of the ergodic matrix product state. So if you'll excuse me, I think I'm going to try to very quickly do this. So if you've never seen matrix product states before, then this is probably a time to tune out, because I don't think you're going to learn it from my very fast thing. But a matrix product state is a particular way to form a state. That these are popular ansatz states for analyzing spin chains, where you take the computational basis of your spin chain, which are just some numbers running through 1 to d. So you spin 1/2 spin chain. They take values 0 and 1, okay, 1 and 2, and you have some matrices attached to each site, and you take the trace of the product of those matrices, and you call that the weight of the state. So they're nice because they have a very compact description in terms of these matrices, whereas an arbitrary state in the Hilbert space requires, well, in this case, d to the n random variables. But here I have a polynomial in d number of, not d to the n coefficients. Here I have a polynomial in d coefficients. And the point about matrix product states is that the expectations in the state are very closely related to understanding a process which is related to these matrices. Okay, that's not something which I'm going to explain carefully, but here's a formula. Okay, so if I want to compute the expectation of an observable, just think that it's a single site observable. I said it lives on an interval, but say it's a single site, it's the spin at a single site or something in this state. Then what I need to do is I need to take the process that the channels that I defined here, which are related to the matrix living in the state, and I need to compose them from one end of the chain until I reach the position of the observable, and then I'm going to do something else. Notice this is an O hat, not an O, because the O doesn't act on the right space. The O acts on the Hilbert space over here, and this O hat does something else, and then I'm going to compose these over here. And I have this capital TR. I've written a capital sign because this is the trace of the super operator that I have written down there, right? Which, after all, is just a linear operator, so I can think of it as a matrix on a space. It just happens to act, the density matrix has dimension d squared, so this acts on a d squared by d squared space, okay? And I can compute its trace. And then I normalize by the trace of the process without the O hat there, okay? And the way I do O hat, if you condense this down to a single spin observable, is I just basically take the matrix elements of the single spin observable, if this is just IM and JM here, and I use the matrices in the right combination to get that, okay? And this is a formula that you can verify for how to compute the expectation in the matrix product state. So obviously, what you see here, if you try to take the thermodynamic limit, is a long chain of operators, and so this is exactly what our theorem tells us about. And so, right, if we have a matrix product state with operations with matrices in it that give rise to these quantum operations that form one of these ESP ergodic sequences, then we can compute the thermodynamic limit. We can take the boundary off to infinity, and we're left with something that just depends upon that invariant, so all the information about the matrix product state is actually encoded in that invariant state, the Z function. Well, actually Z and Z prime, which were the left and right sort of generalizations of eigenvectors. And so there's a formula involving those for the expectations in the matrix product state. And from this formula, you can see that that the local observable, that we have exponential decay of correlations, which is not very surprising that you have exponential decay of correlations, honestly. In fact, I mean, you have this for a typical matrix product state that's translation invariant, and it's not surprising at all that now that we've randomized, you wouldn't expect randomization to give you better more correlation. Okay, but what I wanted to get to, which I'm gonna rush a little bit, and I'm sorry for this, right? So we can talk about the entanglement in the state. So if we, we can cut across the entanglement entropy is the entropy of a reduced density matrix of half the chain, and we can relate that to this to the Z and Z prime matrices. And there's a random variable now which describes the entanglement entropy. The interesting thing is that we can identify two different phases of ergodic matrix product states, with things that satisfy this assumption. One of them basically look like translation invariant. Okay, the entanglement entropy goes up and down because it's a random variable, but it never gets close to zero. Okay, and that's what you expect in matrix product state. Now, the entanglement entropy can never be exactly zero because the density matrix Z is guaranteed to be strictly positive. So we can never get exactly zero for the entanglement entropy, but we can get very close to zero. So there are potentially ergodic matrix product states in which the entanglement entropy does not have a lower bound. As you look out on bonds further and further away, you eventually find one where it's as small as you like. And so I decided to do a quick calculation of this. I went back, used the amplitude damping channels with different amplitude damping parameters. They use what's lambda here. Sorry about how small this is. Was the gamma on the previous slide. And these are the distributions of the entanglement entropy along different bonds in different matrix product states. Sorry about the blue being the same, but you can tell what the order is. And you can see, and I can verify actually that for small damping, there actually is a minimum entanglement entropy. So this actually, you can't really tell from the graph, but this curve really does drop exactly to zero. And there's nothing down here. There's probability zero of getting anything here. And then at some point around 0.7 for the damping rate, there's a transition to states that have a distribution that touches zero. Okay. So it's interesting. I don't know an application of this, but it is an interesting sort of two separate phases of matrix product states. Okay. So yes.
So the entanglement being zero, this means that the state of the joint system is a product state. So
right, but it's never quite a product state. Right. It means that if you go far enough out in your system, you will find a bond on which you might as well pretend it's a product state because the entanglement is,
So the system is kind of
right.
Broken.
Right. And yes. Yeah. What's that? Breakable. Yes. Okay. So I guess, I had some conclusions. I've said most of those things. Let me just leave this slide up here for the end. I talked about some of these. I put some open problems in red. Well, non-ergodic processes is an interesting thing to look at. Reducible processes is what Owen Ekblad is looking at right now. Estimation of convergence time. This question always comes up in physics talks. Throughout this talk, I fixed a finite dimensional system and a process, and I told you long time behavior. Of course, you want to know if I make my system large, what happens? That requires more specific assumptions on what the process looks like. You're going to get different answers depending on the assumptions you put in, and that doesn't follow easily Recently, a colleague, Brent Nelson, and a student at Arizona did an infinite dimensional version of this on a particular class of von Neumann algebras, which is a very nice mathematical result. I don't know about any application to physics, but it's kind of cool that you can move beyond this finite dimensional theory. Okay, and then this is something that would be really interesting. I'm really using a dynamics perspective here. So matrix product states on a spin chain are really all we can talk about. If you're talking about tensor network states in a two-dimensional system, the structure doesn't carry over, but it would be interesting to understand. Okay, and I'll stop here because I've gone a couple minutes over.
Thank you, Jeff, for the very nice talk. We had questions throughout, but maybe time for one or two last final questions, including in the chats.
Well, I have a vague question. So I guess in the beginning of the talk, you said that the assumption of the this is the assumption of the math is kind of generic. So if we do the random mapping, then it's satisfy the problems. I'm just curious how this applies to the last one. To what extent is it generic?
Oh, so there I haven't chosen anything generic because I've taken a specific form, which is the amplitude damping channel, and I'm making only one parameter, namely the damping rate random. Well, and I'm also randomizing the direction that it's. I didn't mention that, but these were chosen on a random direction on the sphere to do the amplitude damping.
So if it's not the specific version, just random. Is there any general result that one can say and it's generic or?
I mean, yeah, of course you do have to say. So the difficulty I always come up when I so. Okay, so that's a different, that's okay. So there are two questions you could ask. Okay, a simpler one is the following. If you take a translation invariant matrix product state, but you choose the matrix, the set of matrices in it randomly, what properties does it have? Right.
And how generic is it?
And that should be very generic. Now, of course, if you, and I actually think there are works on that, and I'd have to figure out who did them. That's not the situation we're in. Do we have people who need to use this room?
We've also got a question.
Oh, okay. Oh, Birgit. But if you want to do this for this disordered ones, now I somehow have to come up with a notion of what a generic disordered ensemble is, which is now I sort of need a probability distribution on the space of possible probability distributions, which becomes a little bit unpleasant to think about. So, but maybe not a bad idea to think about. But I don't know a good way to formulate it, I think is what I'm saying.
Okay, and there's one hand up in the chat. Maybe if you'd like to unmute and ask a question.
No,
Hi. Hello, can you hear me?
Yes.
Hi, good to see you, Jeff. I had a question about this tensor network states that you mentioned. I'm just starting to explore this as well. So do you have any further comments or?
Oh, no, that's just like, that was the last open problem on the list, which is like a complete pie in the sky problem. I have no comment on how to attack that problem. It would be interesting to see a solution, but.
Right. Okay, yeah, maybe we can talk about it in private sometime.
Yeah, that would be great.
Thank you.
Okay, they have the room next, and I think that ice cream, which is melting, so they're thank